Let me ask you a question that sounds simple, but is actually one of the deepest questions you can ask. What is space? I mean, really, what is it? Is it just nothing? The empty gap between you and me and the stars? Or is space itself a thing? Believe it or not, that question has sparked a massive debate that's raged for centuries, and the story of how we've tried to answer it will completely change the way you look at the universe.
So here's the core of the problem. The two big competing ideas. Is space a giant invisible box that holds everything in the universe? Or, if you could magically snap your fingers and make every planet, every star, every atom disappear, would space itself vanish right along with them?
Now, these two big ideas have some fancy names. The first one, the space is a container idea, is called substantialism. It says space is a real substance. The other idea is called relationalism. It says, nope, space is just how we describe the distances and directions between things. And the first major battle in this intellectual war was fought by one of the greatest scientists who ever lived.
To get his laws of motion off the ground, the legendary Isaac Newton realized he needed something solid. He needed a fixed, permanent, unchangeable backdrop to measure all motion against. For him, this wasn't an option. It was a necessity. He called it absolute space.
What he's basically saying here is that there's this ultimate grid of the universe. It doesn't move, it doesn't change, it just is. Think about it. How can you say something is accelerating if you don't have a fixed background to measure it against? For Newton's physics to work, this cosmic stage had to be real. But how on earth do you prove something that's invisible and immovable?
Well, this is where Newton's genius really kicks into high gear. He came up with this incredibly clever experiment, something you could literally do in your backyard, designed to make the invisible forces of absolute space visible to us all.
Okay, so check this out. Just focus on stage 1 and stage 3. In stage 1, right when you start spinning the bucket, the water isn't moving yet. So you have the most motion between the water and the bucket walls. But look at the water's surface. It's totally flat. Now skip ahead to stage 3. The water has caught up. It's spinning right along with the bucket. There is zero motion between the water and the bucket, and yet the water's surface is curved into a deep concave shape. That was Newton's mic drop. The force curving the water couldn't be about the bucket. It had to be about the water rotating against absolute space itself.
For almost 200 years, Newton's bucket was the killer argument. It seemed like an open and shut case for absolute space. But then, people started finding cracks in the foundation, and it all led to a young patent clerk who'd end up completely demolishing Newton's grand stage.
The first big hit actually came from philosophy. Newton's arch-rival, a guy named Leibniz, posed a tricky question. He said, okay, if space is just a big empty box, what reason would God have to put the universe right here instead of, say, 5 miles to the left? Since every spot in empty space is identical, there's no good reason to pick one over the other. Therefore, Leibniz argued the very idea of absolute places is just illogical. Space has to be about the relationships between things.
Then, much later, the physicist Ernst Mach took another look at that bucket, and he said, Newton, you're forgetting something, the rest of the entire universe. Mach's brilliant idea was that the water doesn't care about some invisible, absolute space. No, it feels that force because it's rotating relative to all the distant stars and galaxies. For Mach, inertia wasn't absolute. It was a relationship between you and everything else out there.
And Mach's idea was just the start. The turn of the 20th century was just brutal for Newton's absolute space. Scientists tried to find it. They called it the ether, but a famous experiment came up with nothing. Then, a young Albert Einstein threw out the idea of absolute time. And finally, with general relativity, he came for space itself.
So Einstein didn't just tear down the stage, he blew up the whole theater. He gave us space-time, a single, four-dimensional fabric. In this new picture, things don't just move through space, matter and energy tells space-time how to curve, and that curvature tells matter how to move. Space was no longer a passive backdrop, it was a dynamic, active player in the game. It seemed like the relationalists had won. Case closed, right? Well, not so fast.
In one of the great twists in the history of science, as we started to study the universe on the grandest scales, a ghost of Newton's idea started to creep back in, but in a totally new and unexpected way.
Okay, let's really think about this for a second. If Einstein is totally right and there's no fixed background, then any motion is as good as any other. My movement and your movement are equally valid. There shouldn't be any special or preferred way to be moving in the universe, should there?
So, what is this? 369 kilometers per second.
That's not a random number. In a very real way, that's our speed. But our speed relative to what?
It turns out that's how fast our entire solar system is hurtling through the cosmos relative to the cosmic microwave background. You know, the faint heat signature left over from the Big Bang that fills absolutely all of space. And this ancient light gives us a universal reference point.
This is what's known as the CMB rest frame. Now, it's not Newton's rigid, absolute space. The laws of physics really are the same for everyone, no matter how they're moving. But it is a special frame. It's the one and only frame of reference where the universe looks the same in every direction. So in a funny way, we've stumbled upon a rest frame of the universe after all.
And this story gets even weirder, because modern physics has discovered that the vacuum of space, the very thing we think of as nothing, is not empty at all. Not even close.
You see, we now know that what we call empty space is actually a buzzing, bubbling sea of activity. It's full of quantum fields popping in and out of existence. It's permeated by the Higgs field, which is what actually gives particles their mass. And this is the craziest part. We've found that the vacuum of space itself has a tremendous amount of its own energy.
We call this energy of space dark energy. And it's not just a theoretical idea. It's having a very real, very powerful effect on the cosmos. It's acting like a pressure from within, pushing galaxies away from each other and making the universe expand faster and faster. And that leads to an absolutely stunning realization. If space can push, if space can do something, then space has to be something.
So let's just recap this wild journey. We started with Newton's idea of a rigid passive container. Then Einstein came along and transformed it into a dynamic, geometric field. And today, our modern view sees space as something almost like a physical, energetic fluid. It has a preferred frame, the CMB frame, and its vacuum is jam-packed with energy. We've ended up with a kind of synthesis. Space really does seem to be a real substance, but it's not the static stage Newton imagined. It's alive.
So we're back to our original question, but now it feels so much bigger, doesn't it? We know that space has energy. We know it has a preferred state of rest. We know it has the power to push the entire cosmos apart. We've learned so much about what space does, but we still don't really have a clue what it fundamentally is. And that, right there, is still one of the greatest and most exciting mysteries in all of science.